Hello everyone. In this video, I will be bringing the topic the P block elements. Okay, P block elements is a part of inorganic chemistry. Okay, in P block, we get to see a variety of elements like metals, metalloids, and non-metals. Basically, you will get an idea of each of the properties of these while studying the P block elements. Okay, so in P block elements, it comprises of group 13 to group 18. Okay. The boron family, the carbon family, the nitrogen family, the oxygen family, the halogen, the family of halogens, and the noble gases. So you can see that there is a wide range of elements which belong to the P block elements. Okay. So first of all, we would see the introduction to the P block elements. Then I would tell you each of these families exclusively, the important elements in those families. Okay. Their important compounds, properties. Okay. You need to remember a few of reactions in these in this chapter, okay, because they are what is asked generally, and I would also tell you some of the questions and past JEE questions, okay, so that you can get the idea of the questions which can be asked from this chapter. Okay, so first of all, we will begin with introduction. Okay. Now, P block element comprises of elements from group 13 to 18. Comprises of elements from group 13 to 18. Okay. Now, the group 13 elements are called boron family. Okay, now why are these called boron family? Okay, because in the second period, now this is the second period of the periodic table. Okay, second period we have boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, and then we have in this 13 group, this is group 14, this is group 15, this is 16, 17, and 18. Okay, now in the group 13, okay, boron, aluminium, germanium, indium, and thallium. Okay, similarly carbon, silicon, germanium, okay, and so on. Okay, so now you can see that in this family, the group 13 family is called a boron family because boron is the first element of this family. Okay, boron is the first element of this group. That is why we call this as a boron family. Similarly, group 14 is called what you say carbon family. Okay, group 15 would be called nitrogen family. Okay, group 16 will be called oxygen family. Okay, group 17 is called, it is not called fluorine family because we have a special name for all the halogens: fluorine, chlorine, bromine, iodine, acetylene. Okay, we have a common name for all these halogens, that is, we have a common name for all these elements, that is halogens. Okay, so we call this as a halogen family. And group 18, you very well know, group 18 are the noble gases. Why are they called noble? Because they do not react with other elements so easily. Okay, only xenon is known to be, the compounds of xenon are known. The compounds of rest are very rare. Okay, so they are called noble. So this is the noble. This is the family of noble gases. Noble gases family. Okay, now why are these called noble gases? Because all of them are gases. Okay, now let me give you some example of the metals, non-metals, and metalloids present in this family. Okay, the non-metals Okay, first of all, the non-metals present in this family are very simple. See, boron is a non-metal, carbon is a non-metal, silicon is a non-metal. You all know that the second period, anything of this, any element of the second period is all non-metals. Okay. Now the metalloids. Okay. Now metalloids. Now P block elements also contain. In fact, P block element contains all the metalloids in the periodic table. The metalloids are aluminium, germanium, okay, and so on. Now these are the examples. Now for the metals are indium, thallium, polonium. Okay, these are some of the metals. There are many more we would see in detail when we go into each of these groups. Okay, or each of these families. Okay. Now the salient feature in the P block elements, is that the second period elements of the P block element, that is the first element on which the naming of family is there. Okay, let me again draw this. This is the second period. Okay, the first the elements are boron, carbon, nitrogen, oxygen, fluorine. Okay, all these elements differ from their group elements. Okay, aluminium, gallium, indium, and thallium. Okay, like boron differs from all others. Okay, quite significantly. Okay, similarly, carbon differs from silicon, germanium. Carbon differs from all others. And carbon differs from germanium very significantly. Okay, now what is the cause of this significant difference? Okay, the cause of this significant difference is that the second period elements are very small in size. They have high electronegativity. Okay, and there is no d orbital. Okay, you might know that there are 4 kinds of orbital: s, p, d, and f. Okay, S is the closest to the nucleus. Then there is p, then d, then f. Okay, the proximity with nucleus is S, then P, then D, then F. Okay, S is most closely packed, very near to the nucleus. Okay, now the electronic configuration of boron is 1s2, 2s2, 2p1. Okay, so it is very close to the nucleus. Okay, now let me draw this. First, note down this point that the first member differs significantly from the other members of the group because of its small size, high electronegativity, and absence of d orbitals, d and f orbitals. Okay, now the electronic configuration for boron is 1s2, 2s2, 2p1. Okay, the atomic number for boron is 5. Okay, carbon is 6, nitrogen 7, oxygen 8, fluorine 9. Okay, so the electronic configuration for boron is 1s2, 2s2, 2p1. Okay, but the electronic configuration for gallium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p1. the atomic configuration for indium is, or say atomic configuration for thallium. For thallium, the atomic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 4f14, 5s2, 5p6, 5d10, 6s2, 6p1. Okay, so you can see that the atomic configuration of boron consists only of S and P. Okay, but for gallium there is a d orbital. Okay, for thallium there is d as well as f orbitals. Okay, now you can see that since S is very close to the nucleus, okay, so this has a very small size and the number of orbitals are also less. Okay, they can see there are only 3 orbitals. Okay, so boron is very small in size. Say that this is the nucleus. Suppose this is the nucleus. Okay, and these are the orbitals. This is the s orbital. The s orbital. Okay, so these are the 2 electrons over here for 1s, 2s, 2p. Okay, this is 1s2, this is 2s2, this is 2p1. Okay, this is for boron. Okay, now, but for gallium, okay, you can see count how many orbitals are there. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 orbitals. Okay, so similarly there will be 8 such rings. Okay, so you can imagine that gallium would have a very large size as compared to boron, and thallium would have even more because it has how many orbitals? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15. It has 15 orbitals. Okay, see, you can now very well imagine that the size of thallium would be quite high because it would have 15 such rings and there would be electrons in it. Okay, so it has a very small size. The first member has a very small size. Okay, now due to its small size, okay, it has very high electronegativity. Okay, what do you mean by high electronegativity? By high electronegativity, we mean that it has a tendency to accept electrons, okay, or attract electrons towards itself. Okay, now since boron, the shells are quite near to the nucleus. Okay, these are the shells which are quite near to the nucleus. They tend to attract the nucleus tend to attract electrons towards itself. Okay, so it would have a very high electronegativity because of its small size actually. Okay, the size is small, so it will have a high electronegativity because the nucleus will have a tendency to attract electrons of the boron towards itself as well as of the other elements which would come near to the electron. Okay, because there are only 3 shells present, so the effect of nucleus would also be outside these shells also. But in case of gallium and thallium, the shells are too many. Okay, so the effect of nucleus diminishes. Okay, the nucleus effect vanishes within the cells itself. Okay, within the rings itself. So it would have the electronegativity decreases when we go down the loop. The electronegativity when we go down the loop, the electronegativity decreases because the size of the elements, okay, or the atomic radii increases. Okay, so since boron is the smallest in size, therefore it would have highest electronegativity in this group. Okay, we would say electronegativity is inversely proportional to atomic radii. Okay, electronegativity is inversely proportional to atomic radii. As atomic radii would increase, electronegativity would decrease. Okay, so boron has high electronegativity, and similarly the other members of the same period, the second period, carbon, nitrogen, oxygen and fluorine, would have the same property. They have a very small size. Okay, again for carbon, yeah, or say nitrogen. For nitrogen, the electronic configuration would be nitrogen. The electronic configuration is 1s2, 2s2, 2p3. Okay, you can again see it is number of shells remain 3 only. Okay, so these properties would again hold for nitrogen. Similarly, they would hold for carbon also, oxygen also, and fluorine also. Okay, now absence of D and F orbitals, you can very well see that in the electronic configuration for boron there is no D orbital. Similarly, for nitrogen there is no D orbital, but for gallium and thallium there is D as well as there is F orbital. Okay, therefore the first member differs significantly from the other members of the group. Okay, now the next thing which again significantly varies or is significantly different is that the first member of each group has greater ability to form p pi bonds with itself and or other elements of the same period. Okay, so what do we mean by this statement? That each member, the first member of each group, okay, like consider for example carbon, has the ability, greater ability, in fact it has the highest ability to form the p pi bonds with itself. You are very familiar that the bonds like C double bond C, C triple bond C, or C triple bond N, C double bond O. Okay, you are very familiar with these bonds. Okay, but you are not familiar with the bonds like Ga double bond O. You are not familiar with this because these bonds are very rare. Okay, these are generally not formed. Okay, but these are formed. This bond is formed. This is formed. This is also formed. This is also formed. Okay, so what happens is that the first members, okay, have a greater ability to form p pi bonds. Now you know that this is a pi bond. Okay, this bond over here, this is a pi bond. Okay, similarly these two bonds are also pi bonds. Okay, now why do they form and pi bond? You know that pi bond is formed by use of p orbitals only. Okay, so they are able to form p pi bonds owing to again their small size. Okay, but as the size increases, the tendency to form p pi bonds decreases. Okay, now this is again a special feature. Now you can see that this forms bonds with itself. It forms bond with other elements of the same period. This is the second period. Okay, so carbon forms p pi bonds with the other elements, nitrogen and oxygen, of the same period. Okay, now the other feature is of P Block elements. The other feature of P block elements is the highest oxidation state of P block elements is group number -10. Okay, the example is, okay, now consider for example boron. The group number for boron is 13, for carbon is 14, nitrogen 15, oxygen 16, fluorine 17. Okay, now the highest oxidation state, okay, for these elements or these groups, okay, is what? The group number. Okay, so what is the group number? Consider for example for boron family. For example, you consider the boron family. For boron family, what is the group number? The group number is 13 minus 10. So highest oxidation state is 3. Okay. Consider for example the nitrogen family. Okay. The group number is what? 15 minus 10. So the highest oxidation state is 5. This is plus 3 and this is also plus 5. Okay. So this is the way how we calculate the highest oxidation state of P block elements. It is actually group number -10. Okay. It may vary in some cases, but it is the highest oxidation. Its oxidation state cannot increase. For boron family, it cannot be more than +3. For nitrogen family, it cannot be more than +5. This is the highest. It can be less than it. Okay. Now, another feature is that of an inert pair effect. Okay. We would see inert pair effect in detail in the next videos, but let me just introduce you to it. The next feature is of inert pair effect. What do you mean by inert pair effect? Inert pair effect is the reluctance of valence s orbitals electrons to take part in chemical bonding. Okay, so by inert pair effect we means the reluctance of the valence s orbital electrons to take part in chemical bonding. Okay, now you know that s, the occupancy, the maximum occupancy of s orbital is always 2. Okay, it is 1s2 or 2s2 or 3s2. Okay, it is always 2. Okay, 1s2, 2s2 or 3s2. So it is always 2. Okay. Now since these electrons are 2, therefore we call it inert pair. Okay. Now what happens is that in the P block elements, okay, I told you that the highest oxidation state is group number -10. Okay, but as we move down the group, okay, like when we move from down the group from boron, aluminium, gallium, indium and thallium. Okay, so as we move down the group, okay, when we move down the group, the highest group oxidation state is not group number -10, but it is 2 less than that. Okay, when we move down the group, so when we move down the group, the highest oxidation state tends to be 2 less than group number minus 10. Okay, so for thallium, okay, for thallium, what would be the highest oxidation state? We calculated that for boron family, the highest oxidation state was +3. Okay, so thallium will have a tendency to have highest oxidation state 2 less than +3. That means for thallium the highest oxidation would be +1. Okay, now this tendency of having +1 oxidation state instead of +3 oxidation state increases when we move down the group for all the families of P block element, that is for boron family as well as for carbon family, for nitrogen, oxygen as well as hydrogen family. Okay, all the elements have this tendency to have highest oxidation state 2 less than their highest oxidation state found by this formula. Okay, because of inert pair effect. Okay, now what actually is inert pair effect, I will tell you in detail in the next video. Okay, for the time being, you just need to remember that when we move down the group, the tendency to have highest oxidation state, the tendency to have highest oxidation state -2 increases when we move down the group. Okay, basically the highest oxidation state is found by this formula, but the actual oxidation state for when we move down the group would be 2 less than this. Okay, this is the important point which you need to remember, which is followed by all the families of P block element. Okay, so that's all for this video.